everyone, and welcome to Astropod, the astronomy podcast series conducted by the Astronomy Club of the University of Sri Jayewardenepura. We are delighted to have you with us today as we explore the universe through engaging conversations about space, science, and discovery. For today's episode, we are truly honored to be joined by an exceptional physicist and science communicator, Dr. Purnima Narayan. Dr. Narayan is currently an academic professional in the Department of Physics at Arizona State University, USA, where she contributes as an online lab instructor, provides instructional support, and actively engages in departmental outreach. She recently completed her PhD in physics at the University of Mississippi, where her research focused on gravitational waves and testing general relativity, particularly exploring how biases and missing physics can influence our understanding of the universe. Dr. Narayan is also a member of the LIGO Scientific Collaboration and the LISA Consortium, contributing to groundbreaking research in gravitational wave astronomy, one of the most exciting and rapidly evolving fields in modern astrophysics. Her work has been widely recognized through numerous awards, including the 3-Minute Thesis Grand Prize, International Graduate Student of the Year, and multiple honors for excellence in research, teaching, and community engagement. We are incredibly excited to have her with us today to share her insights and experiences. And at the same time, joining me today as our host, Ms. Kulamini Amarathunga, who will be leading this discussion with Dr. Purnima Narayan and guiding us through an engaging conversation on gravitational waves, their detection, and what they reveal about the universe. So once again, welcome Dr. Narayan. It's such a pleasure to have you with us today. Thank you for joining and welcome to our host as well. And to our host, take it away.
Yes, thank you, Ms. Sonagi, for the introduction. And thank you, Dr. Purnima, for joining us. It's such an honor to talk to you. And so today we're discussing gravitational waves, which I think is representing one of the most significant developments in modern physics. And for a long time, astronomy was entirely based on, electromagnetic observations. But today, we are directly studying changes in space-time itself, which is absolutely amazing.
Yeah.
And so I'd like to start from the theoretical side and then build up from over there, if that's okay with you.
Yeah, that sounds like a great plan.
Yeah. So as a student who is still learning, not an expert, the idea that I have in my head about gravitational waves. So I think it was first predicted by Albert Einstein back in 1916, and it was through the theory of general relativity, and where accelerating masses produce, time-varying, somewhat curvature in space-time. So could you help clarify that? What exactly are gravitational waves, and in physical terms?
Yeah, sure. So first of all, thank you for this opportunity. I'm really excited and looking forward to chatting with you about gravitational waves. It's one of my favorite topics to talk about. So as you correctly said, gravitational waves were first proposed by Einstein in the 1900s. And it is so exciting and it is groundbreaking because we took 100 years to detect these ripples or these curvatures in space-time. So it is indeed groundbreaking today, even talking about it. So going into what gravitational waves are, let me start by giving you a picture or a physical idea, and then I'd like to go a little bit into the math of how it is derived from Einstein's equations. So first of all, I want you all to picture this. So imagine there is this large mesh of space and time, like how it's in the background, that's going all across the universe. And we can only talk about gravitational waves in Einstein's framework. We know that we have different different theories that explain gravity, but the theory that we'll be talking about today, just to clarify, is Einstein's framework of gravity, in which he says that gravity is nothing but a manifestation of geometry, which is space-time is the geometry, and then masses or energy tell the space-time how to curve, and in turn, the space-time will tell the mass or energy how to move or accelerate. So having this framework in mind, we would then likely describe gravitational waves, which is this large mesh of space and time that is going across the universe. And now, if you have accelerating masses in this space time, let's say I have two spinning balls in this space time, and they are like constantly spinning and like in really high speeds or really high velocities. So when this happens, you can imagine that it's going to cause disturbance in this mesh, and it's going to distort the mesh, which is initially calm and quiet. So that disturbance, which is like happening on the mesh, propagating across the mesh because of these little spinning balls or little accelerating objects, that is what we say as gravitational waves. Now, there are two terms here, right? One is gravity and one is waves. Waves, because it's similar to what you see on a pond. So you're going in a pond, you're throwing a pebble, and you see these nice waves, right? So that is why it's waves and why it's called gravitational waves, because we explain gravity as the curvature of space-time. And since the space-time itself is getting distorted, we call them as gravitational waves. So this is likely the physical or like a picture of what gravitational waves are. But mathematically, these are waves that come from Einstein's equations. So Einstein's equations are these really complicated, very nonlinear set of multiple equations. But once you put certain assumptions into that and we try to simplify the equations, one of the solutions to these Einstein's equation is a wave equation. And that wave equation is the gravitational wave that we talk about.
Oh, okay. Okay. So when people talk about gravitational waves, I've always heard this term ripples in space-time.
Mhm.
What do they mean by that?
So it's exactly what it says. It's like, what do you mean by ripples in water or ripples on in a lake or in an ocean or in a pond? It's the exact same thing what you say as ripples in space-time. The only thing is instead of water, now you have this imaginative structure of space-time around you. So when you say ripples, it means disturbance. It means passage of energy. It means distortion. So what is happening is in this calm set water or like a calm pond or a calm space-time background, something violent is happening and that is distorting this calm background and the energy is being transferred. And this transfer of energy is called the ripples of space-time. So
Okay, so it's like it can pass through space itself, like it doesn't need any medium or like it can pass through
yes.
space.
Yeah, so it is the passage of the space-time itself. So now we'll be talking about space and time as one entity because that's how Einstein's theory defined it. So it is passing through space-time on space-time. So it's like the space-time itself is being distorted. Well, I can give you like an easier picture for you to better understand is that say for example, what will happen if a gravitational wave is passing through me right now, or what happens if a gravitational wave is passing through you. So since we are all part of this space-time and we are sitting on this space-time, the passage of the gravitational wave is going to distort the concept of space, right? Which means it's going to distort my body in some way. It's going to elongate my body and then squeeze my body. So elongate my body and squeeze my body. So it's going to create this distortion through space or through things that it passes through.
Okay, okay, that actually makes sense. So
Okay.
do they have the speed of light and like carry some energy away from systems or like into systems?
Yes, so they definitely carry energy away from systems, and that is how we were able to first strongly predict that gravitational waves exist after Einstein's proposal. And yes, so currently gravitational waves are I mean, we so far, with the information that we have, we can see that gravitational waves are traveling with the speed of light. But I know we'll come into this later, but when you talk about theories of gravity, or when you talk about alternative theories of gravity, there is still an open question, is if indeed gravitational waves are traveling with the speed of light. But as of today, all our evidence prove that it is traveling at the speed of light. So we'll keep it at that.
Yeah, so taking a step further. So when we talk about forces, like electromagnetic force and whatnot, we always integrate a carrying particle into it, photons carrying the electromagnetic force. So likewise, are there any like particles, I mean, gravitons? There's a concept for gravitons. Is it actually real or do they exist?
It depends on who you're asking, and it depends on what theory we're looking at. So
Okay.
there are certain theories which says gravitons are existing and gravitons have mass to them, and those would be the ones that are generating gravitational waves. Whereas there are certain theories that might say there are gravitons that have no masses and they have nothing to do with gravitational waves. So it depends on who you're asking and which theory they believe in. So that is again an open question. It's a very good question, and still an open question. But since you're talking about electromagnetic waves, as you rightly said, it's because of some particle like electrons or protons. So the idea that would want a listener to develop is that the electromagnetic waves are generated due to some acceleration, due to some particle going back and forth. It is some oscillation of charged particles, right? So now, similarly, when you have gravitational waves, you also need some sort of acceleration. So it has to have some sort of accelerating asymmetrical motion, which would cause these gravitational waves. Yeah.
So if gravitons were real, if they actually existed, could we like at some point detect it maybe using the Large Hadron Collider as they found the Higgs bosons there? Is it possible?
I think so. Yeah, I don't see a reason why not, because science and technology is getting so advanced now that it's very hard to say this is not going to be possible. So
Right.
and again, so it's not about do gravitons exist or not. It's about do gravitons carry energy? Do gravitons have mass? That's the question. I mean, if they exist and they have no mass, no energy, then what are we talking about, right? So if the question is, do gravitons have mass? Are they carrying energy? Are they the fundamental particle for gravity? So, like, those are the questions that we might have to answer. And one way to find them is using these high energy experiments like the Large Hadron Collider. And another way to look at is another region of high energy collisions or high energy phenomena like black holes, or during like cosmological things that are happening. So like there are different ways that we can get to the question of gravitons. So yes, I would definitely say if they have mass, or if there is more to gravitons, we would definitely be able to get to that in the future.
Mhm. That would be very interesting to find.
Yeah.
It's such groundbreaking news. And
Yeah.
so, from what I understand, you need accelerating masses with some level of asymmetry. Let's say,
Right.
for example, let's say binary systems. So, could you explain what conditions are required for a system to produce detectable gravitational waves?
Yeah. So let me talk about why do we say detectable gravitational waves, and why can't we detect all gravitational waves? So first and foremost, we need accelerating bodies, right? And accelerating bodies that have masses associated with them. So when we say the sun and earth, and when the earth is going around the sun, that's also some sort of acceleration. So that system would also produce gravitational waves. So, like any accelerating system will produce gravitational waves, but as you rightly said, they may not be detectable. And the reason for that is the amount of distortion that gravitational waves are producing when they are passing through an object is extremely, extremely small. So you need to have like really either massive systems or systems that have moving with really high velocities. So like these extreme systems to produce higher distortion that we can actually detect with the current detectors. So then when you talk about detectable systems that produce gravitational waves, one of the most extreme system that is producing gravitational waves that's easy for us to detect are binary black holes, like you said, like a binary system. That means like two black holes orbiting around each other and then finally colliding and merging into one. But does not necessarily have to be black holes. It can be a black hole and a neutron star, or a neutron star and a neutron star, or even a supernova, or even pulsars. And there are like a lot of other different kinds of sources, but like these would be the top sources that produce gravitational waves that can be detected with the current detectors.
Mm.
But with the advancement of technology, of course, things will be advancing and changing.
Yeah. So in 2015, I think it was the first time we detected gravitational waves, and it was a merging of two black holes
Right.
were detected. But
Yes.
so that was a specific event, right? I mean, the merge, it was a specific event. So are there like any continuous events that is happening? You mentioned about pulsar. So if that's the case,
Mhm.
is it continuous, the gravitational
Yes.
wave?
Yeah, definitely, definitely. So, as you rightly said, in the term that we use for these sort of gravitational wave systems are called events. So, like each passage of gravitational wave that we detect is called an event. So the ones that they have discovered or that ones you have detected so far are these transient events or like
Yeah.
smaller gravitational wave events. And there are definitely continuous gravitational waves, like you said, pulsars, because they are accelerating and pulsating. They do create these continuous gravitational waves. But what is most exciting for me in like that regime is the gravitational waves created in a cosmological scale. So during the Big Bang and during the evolution of the universe, there were still gravitational waves that were produced, which have a potential of being detected.
Mm.
So we call them as stochastic gravitational waves, which means they are everywhere and it's not easy to resolve them. It's not as precise as a gravitational wave coming from two binary black hole. So that's like a challenging aspect of the cosmological wave. So yes, so answering to your question, there are these smaller signals which are small and crisp and defined, and there are these continuous and stochastic signals that are a little bit more challenging.
Yeah, so when you said that it's like it could be something in the background, like everywhere. Is it like the CMBR that we
Yes,
detect? Oh,
yes,
okay,
yeah.
okay, it's very interesting. So as I
Mhm.
understand, at LIGO in
Yeah,
2015, how we detected that was using two perpendicular arms that were like 4 kilometers in length, and we just it sort of like the gravitational wave passed through
mhm.
the arms, and it slightly stretches when it is traveling, and one arm is stretching and the other is like compressing the other,
Mhm.
and that's how we detected it. Can you like explain how we're doing it? It sounds really interesting and sounds impossible at the same time because it's really small scale.
Yeah,
I heard somewhere someone talking about this, like the measuring the distance, that is the fluctuation in space time that's happened by the gravitational wave passing is sort of similar to what is we measure from let's say we are measuring the distance from Earth to Alpha Centauri, and then we are trying to measure the distance of a human hair, like the width of a human hair. It's very very small, and like let's say 10 to the power negative 21, that
yeah.
is extremely small and even very small than the proton itself. How is it possible even?
Yeah, so that the reason why it feels so impossible is the reason why it took us 100 years to be even able to detect it. I mean, people are going through so many breakthroughs, they have to come up with so many ideas. So first thing they had to believe that gravitational waves exist. And then they had to be creative in like coming up with technological aspects on what could be done in order to detect something that is so tiny. And as you said, yes, the disturbance that is caused is very, very tiny. It's of the order 10 to the power minus 21, and that is even smaller than the size of an atom. So it's like really, 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 really tiny. So yeah, so the even to me, even thinking about having LIGO detect such a small disturbance still is unbelievable. Still, it feels unbelievable and impossible, but we have done it. So getting into that, the concept or the technology that's being used there is a very simple concept. It's just what we have done in our undergraduates is interference of light. So they have taken a very, very simple concept of interference of light and then like increase the scale of it and then use that as a detector to detect these ripples of space-time. So let me start by going through this detector. So we said we have the L-shaped detector, right? So each of this is one arm, this is another arm, and each of that is 4 kilometers. So what happens is, imagine you have a circular ring, and you have a circular ring of particles. And now, when a gravitational wave is passing through it, this circular ring is going to become an ellipse. So it's like stretching, compressing, stretching, compressing. And now imagine you have some object here and you have some object here or here. So, right, so when it's stretching, this object is going to move back and forth, and this is compressing, this object is going to move back and forth. So this is going to move like this, and this is going to move like this, right? And now what I want you to imagine is having the L-shaped detector with one arm coming from here, one arm coming from here. So what is happening is at the end of this L-shaped, we have some object which are mirrors, which are really massive mirrors. And what we are doing is when the gravitational wave is passing, these mirrors are going to have some small movements. And then in the center, we have a laser, which is flashing light into these two arms, and it's reflecting from the mirror, coming back and going on. And as we have learned in physics in our undergrads and so on, the interference of light produces certain pattern, produces some constructive and destructive interference pattern. So if we can calibrate our detector such that we have a complete destructive interference, then if there is some movement which is causing some change in the interference pattern, that means we have some signal or like something is moving these mirrors which are causing this change in the interference pattern. And this is the technology that is being used in LIGO, with the use of which we have detected gravitational waves. And this is especially, as you said, like the strain is so small, it's 10 to the power minus 21. And that is the beauty of using light. The light is, again, it's light can be explained in terms of quantum theory as well. So that is a beauty of light, that we can make these precise measurements using lasers. And that is what we are using to make these like really precise measurement of 10 to the power minus 21.
So it's the laser that is stretching and like it's sort of
It's the mirrors move that are moving. So if this is the L shape and here and here we have these two mirrors, it's this mirror that's going back and forth and this mirror that's going back and forth. But the interference pattern that is produced by laser, that is so precise that if there's any change in that interference pattern produced by these lasers, we
lasers.
can, yeah, then we can know that it's because of some distortion happening in the at the mirrors.
So the lasers also has to be like incredibly stable in order to do
Yes.
that.
Yes. So it's a huge, so when I'm talking to you, it seems like very simple. It's just like pointing a laser to a mirror, but no, it's definitely not that simple. We have to do a lot of technological um, techniques to reduce the or to make the lasers more stable. or to make the lasers more sharp. We don't want any noise, or we don't want any other disturbance. So like there is a lot of other things that go on from the instrumentation point of view, which are making this possible. So it's definitely not as simple as shining a laser and coming back and getting the interference done.
Yeah.
Yeah.
So how do we know that it is not just a random noise that is, let's say, just from
Yeah.
neighboring grounds, let's say? How do we
Yeah.
know?
Yeah. So there is a joke that goes in our community that even so when we have these squirrels that go up the trees and they drop these little
Yeah.
nuts or like little fruits on the ground,
Uh-huh.
even a leaf, even like a rumbling leaf that falls on the ground, even that can cause a distortion in the laser. So that because it's so sensitive, right? So that's a great question. So what goes on is we have to characterize, we call it noise characterization, which means we make a noise profile. So we would already figure out what is the level above which, if we get a signal, that means it has to be noise. So, say for example, we know that the amplitude of the distortion is 10 to the power minus 21, right? That means any noise that's coming above that number, say above 10 to the power minus 19 or so, those would be our noise. So anything that is causing the disturbance above that would be noise. That is one way. The other way to do it is to find out the nature of this noise. Say if this noise is happening randomly and then does not happen ever again, or it's just like so if a detector is detecting and it's just like a blip and then it goes away. So when we have um, these kind of signals, we know that it's definitely not physical. It's definitely not coming from a physical system. So then we can rule them out. So there are like these several different techniques that we can use in our analyzing the data that can separate the noise compared to the actual signal.
Mm. It's actually funny because remember when CMBR was found? I think it was
Yeah,
at the Bell Laboratory. Yeah,
yeah,
they
yeah.
thought that it was just
It was by coincidence. Yeah,
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 yeah. Could be,
exactly.
could have been a similar
I think,
event.
yeah. Mhm.
Yeah, so
Science and breakthroughs happen in all sorts of funny ways. So,
yeah, I bet even scientists at LIGO must have thought that it was a random noise at first when they saw the signal because like it's
yeah, yeah. And the funny
unbelievable.
thing is, LIGO was not the first idea of detector. There were people before that who made different types of detectors and said that they detected gravitational waves. So, LIGO was just a detector that worked and that was developed on the basis of this previous detectors. So it was a long effort put by different kinds of people.
That's groundbreaking. I remember it was 2015 when the news came out, and I actually didn't believe it. I didn't think it was real. At the time, I didn't even know that black holes existed because
Oh, okay.
there were no
Mhm.
photos until
Yeah.
2019. So,
Mhm.
yeah, so once the signal was confirmed, it was like
Yeah.
groundbreaking. Everybody was
Yeah.
like,
Yeah.
were you
I
there?
remember. Yeah, yeah. So I remember that also very distinct because I was in my final year of my undergraduate degree, and I was a part of some outreach program, and that's when, so it was a coincidence that this news came out, and I was a part of this outreach event where all the students had to present posters on gravitational waves to tell the public that something has happened and how or how India has participated in this detection, how it's like a huge thing and all. So that was my first time when I learned about that. And it was almost like love at first knowledge or like love at first read because it was the first time I learned about gravitational waves and I was like, oh my God, this is, I can, yeah, I lost my mind and I was like, this is exactly what I want to study. So that's how it happened as well.
Oh gosh. So, from what I understand, by analyzing the waveforms, we can extract the properties like mass of the objects and their orbital behavior, or like even the distance, if it is possible. So, how does that process work in practice?
Yeah. Again, it's very easy for me to tell that, oh, this is what happens, this is how it's detected, this is how we get the data, and this is how we are saying that it's a black hole. If not, it's a neutron star. So all of these things I can just hand-wavingly explain it to you. But again, the background work can be lots of data, analyzing data, lots of computational efforts, lot of people going and like doing tiny technical or instrumental modifications. So there is like so much background work going on. But to give you a overview of how we do this data analysis, so the first thing is our detectors will detect this signal, right? And when I say signal, what do you mean by a signal? So now when we have black holes that are orbiting around each other and then finally merge, there is a very distinct waveform that is generated. And the distinctness of the waveform is because it starts slowly. And then, as the black holes come closer and closer, it starts increasing in its frequency and amplitude. And then, when they merge, they'll have a peak, and then they'll again die out when they are like when the black hole has merged and like has lost its energy. So, this particular pattern of gravitational waves is what we call a signal. And this is what we want to detect. And this signal is what we use to extract information about the system. And the way we would do that is first numerically and mathematically. Say I take an array of masses from 10, we call the masses of black holes in terms of the sun's mass, which is solar mass. And when I say 10 solar mass, it means 10 times the mass of the sun and hundreds and so on. So if I say 10, 11, 12, 13, and I go until 100 solar mass of one black hole, and then 10, 11, 12, 13, I go to 100 solar mass of another black hole. And then if I ask my computer or my code to give me the gravitational wave signal for each combination of black holes, I can create this nice template of how my signals are going to look for each black hole combination. They can be at different distances, they can be different masses, there are like so many different parameters. And then when I receive this actual signal, what I would do is match my data with these templates that I have. And once I match them with these templates, the one which has the perfect match or the best match, then I would say, okay, this data or this signal has matched this template. That means this system should have these parameters.
Mm.
And that's how, using some statistical analysis, we would then put constraints. So when we say we can tell the mass, we can tell the distance, always in a range. It's always with a boundary of some error level. I cannot say that this black hole is 150 solar mass period. So it has to be like some range, and that's the best we can do. And once we compare this, we would make some sort of probability distribution of how the mass is and what is the range. And that's how we can give the masses, the distance, the orientation of these black holes, the orientation of the orbit, and like all these different information.
Okay, so it's like we have some sort of parameters, and then we predict a certain behavior of a certain event. And if that prediction matches the event that we have
Yeah.
detected, then we say, okay, that is it.
Yes, correct.
Okay. So in terms of theory, gravitational waves provide, a test to the general relativity, as you mentioned earlier.
Mhm.
So under extreme conditions, how are the Albert Einstein's predictions about general relativity and his theory matching to the recent observations and detections?
Yeah, so this is my most favorite thing to talk about because my thesis during my PhD was all around testing Einstein's theory of gravity. So again, we call it Einstein's theory of gravity because it's still a theory, right? We never call it as the law of the universe. It's still a theory that's being tested, but this theory has satisfied and obeyed all the tests so far, because of which we strongly believe in them. which means when we are exploring new sources, for example, this black hole binary was not being able to we were not being able to spot these black hole binaries using electromagnetic telescopes, right? So this means this is a new source of information that we have. And that means we have a newer way of testing Einstein's theory of gravity, or even other theories for that matter. And until today, the kind of sources that we have detected, all of those still obey Einstein's theory of gravity. So we do not have a strong evidence of his theory being violated. Since any evidence of violation of Einstein's theory is going to be huge, it's going to be, again, groundbreaking, it's going to question a lot of things, and it's going to change the way we look at gravity and everything. So we have to be extra careful in when we say something is obeying or disobeying Einstein's theory of gravity, we have to be extra careful. So that means there is still a lot of background work that is going on and still needs to be done before we can come to a point where we can say, you know what, if we observe this, it means it's a violation. So it's still a lot of work until that point, but the detection of gravitational wave itself is like a huge or very novel tool that we have, which we can put to use in this case.
Yeah, I mean, it's very difficult to disprove some theory like that. I can understand it. And I just remembered the first time that we sort of let's say proved the theory of gravity that Einstein proposed, because at first we were thinking that Isaac Newton's theory was the right theory, which he explained that two masses create the attraction, and then Einstein came around and he was like, no, it's just the space-time curvature. And so I'm having a very hard time understanding it in the 3D space. In 2D space, I can imagine it, but do you have like a proper way to explain it in the 3D way, the gravity?
Yeah, so okay, the biggest difference is, let me give you an example. So I don't know, you as physics students, we have probably heard this example a lot, but still for the audience, I can just reiterate it, is about the Earth and the sun. So the question is, if the sun loses all its energy and goes away, when will we know on Earth that it's gone?
It's after.
Yeah, according to Newton's theory, it's going to be instantly. If the sun goes off, you'll instantly know. But according to Einstein's theory, it's going to take a few minutes for us to realize that the sun is gone. That means gravity is taking some time to propagate its information to us. And that is because of this concept of space and time. So again, going back to my illustration of space and time as this mesh. Now, if I put a big basketball, or say even the sun, in this mesh, it's going to create a curvature, right? And now, if I put a table tennis ball or like a golf ball, and if I put this golf ball in this sort of curvature, it's naturally going to start coming towards it. So that means its gravity is being the pull that we feel, that Newton said, if I am here and if my water bottle is here, oh, is it C? Okay. So we also feel the pull towards each other, right? According to Newton, and that's going to be an instant pull that we feel towards each other. But according to Einstein, it means that gravity is also propagating through the space-time. It's not an instant force. And the way he explains it is really beautiful, is that you have this space-time curvature, and his creativity and his thought and imagination is so amazing. I still can't believe how he even came to this point, is that he explains gravity in terms of geometry. And that is mind blowing to me. So when I say moving geometry, and if like distortion of the space time geometry, that itself is gravity. So when we say the sun has a huge gravity, that means the sun has a huge distortion to the space-time. And when you say Earth is going around the sun, Earth is being pulled by the gravitational wave, gravitational attraction of the sun, it means the space time is curved and Earth is in this curvature created by the sun, and that's why it's feeling this pull towards the sun. So that's the way I can best explain
Yeah.
in 3D how Einstein's theory of
Yeah, the
gravity works.
same way the Earth is creating a curvature around it,
Yeah.
and that's how the moon
And
is
there's
moving.
ER. And also us, like we are also in this well of curve. We're also in this curvature because we are attracted to Earth.
Oh, okay.
So we are also being affected by the curvature of space-time exerted by Earth.
Whoa. Okay.
Yeah.
I didn't think about that up until now. I was
Yeah.
only thinking like, okay, the Earth is creating this curvature and the moon is orbiting
Oh
around it
yeah.
because of it. But
Yeah.
yeah, it's true that we are also impacted by it, and that's
Yeah.
why we
Yeah.
are attracted to the Earth.
Exactly. Yeah.
Wow. Okay,
Mhm.
so looking ahead, current detectors are extremely, sensitive to data and everything. So, what are the main limitations that we have in current detections and the technologies that we use currently?
So one of the major limitation is the size of Earth and the amount of space that we have. So let me give you a little mathematical explanation behind this. So when we see the distortion that can be measured is given as a relation of delta L over L, where delta L is the change in the length of this L-shaped detector and L is the length of the arms themselves. That means if we want the distortion or the strain to have a larger value, we want the length also to be larger and larger, so that we can we can explore smaller delta L's, right? So that means the larger the length of the arms, the better it is for us. And the limitation is we are on Earth and we cannot have such large arms. So that is one of the obvious limitations. But there are future detectors that are going beyond this limitation. For example, there are some detectors that are being designed and soon going to be implemented where the length of the arms are going to be around 40 kilometers, which is 10 times more the current length. And there is also a detector that's going to go in space. That's a whole new project. And there, the length, so that's a completely different concept. I don't know if we have time, we might come back to it later. But there, the distance between the two arms is millions of kilometers because it's like out in space. So you have much larger space. So, first limitation is space and length of the arms. The other limitation is noise. Again, because we are on Earth, we are prone to seismic noises. We are prone to all the noise around us. So, this elimination of this noise becomes a huge task. So, these two are like the biggest limitations that we're facing technologically currently.
So, remember when they created this combination of different telescopes as the Event Horizon telescope to get the
Yeah, larger
photograph of the
baseline.
black hole? Would there
Yeah.
be a strategic way to like detect these as well using that type of a technology? Maybe in the future.
Yeah, definitely. So the thing is so let me give you a comparison of what's happening with Event Horizon and with what's happening in that. So Event Horizon is detected by radio telescopes, right?
Mhm.
And then when we have these different telescopes all across Earth, all of them are acting as this large radio dish or like a
Yeah.
huge antenna, and which is looking towards the sky and which is being pointed towards the black hole. But now what is happening is when we have different detectors, each detectors detect the signal at a given time.
Mhm.
It's not possible for us to consider this as if there is somewhere on earth it's like this, somewhere on earth it's like this. It's not possible for us to say let's just match
All right.
these two. Yeah, it wouldn't work that way. But what would work instead is I have one detector somewhere in US. I have one detector somewhere in Europe. Both of them independently are looking at the sky and independently recording the event. Then we can use the information that is recorded at each of this detector in order to figure out where on the sky is this signal coming from. So when you talk about the localization of the source or pointing out the area from where this is coming, that is when the network of detectors on Earth is going to be helpful.
Oh, that makes sense. That makes a lot of
Yeah.
sense. Okay, so in the future, maybe including space-based observations, like you mentioned, uh,
Mm.
what new kinds of sources are we hoping to detect?
Yeah. So this is a very broad question because the universe has so many such huge variety of objects, right? And all of them, or not all of them, anything that produces this asymmetric motion or accelerating motion is going to be a source for
Mm.
us. But even when you talk about just black hole binaries, there are a range of black hole binaries. They can be the size of the sun, to they can be like 10 to the power 6, 10 to the power 9 times the mass of the sun. So we have this huge range of black holes that can be observed. And in whichever range these black holes lie, they produce different frequency of gravitational waves. So the way this works is LIGO has a specific sensitivity range to certain frequencies. It can only measure frequencies from some one limit to one limit. So any black hole combination or any black hole neutron star combination that produces frequency in this range, that will be the only range that is detected by LIGO. Now, when we come up with newer technologies or more sensitive detectors or larger detectors or even space-based, the frequency range is what is changing. The sensitivity is what is changing. That means we'll have different combinations of black holes that can be that the signal from which can be detected. And a big plus or a big advantage of gravitational wave detectors in this aspect is that some of the black holes are theorized to not exist. For example, there are certain mass range of black holes which, according to the known physics, should not exist. But with gravitational wave detectors, we are able to detect them. So that's a big achievement for us. Similarly, we have some other sources, like, for example, we talk about the cosmological sources
Mhm.
from the CMB and so on. We have some things from pulsar, we might have from supernova explosion. So, all of these different kinds of sources would be able to be detected using these different type of detectors. But one thing that is going to be very exciting is we have something called as next generation detectors, which means LIGO after LIGO. There are certain detectors on the ground, which are going to be these 40 kilometers and 20 kilometers and all these arms. And all this information is going to help us to detect around 99% of black hole binaries in the universe. So, how many ever black hole binaries are there in the universe? We are predicting to be able to detect 99% of those. So just imagine the large data bank that we're going to have in the future. So
Wow.
yeah.
100%. That's
Yeah.
a lot. It's unbelievable. Oh my
Yeah.
God. Wow. So I'm particularly interested in these early universe signals as we
Mm.
talked about CMBR earlier. So is there
Mhm.
a realistic potential for us to detect, uh, primordial gravitational waves that will?
Yeah, for sure. Yeah, there is already a group that is working on this. They are called Nanograph. So they are already working on this, and I think they have had a breakthrough recently where they have found a signature of these stochastic signals. So there, it is very realistic, and there's already a lot of progress that's happening there. So you can look up a nanograph. Unfortunately, I'm not an expert in nanograph, and I don't exactly completely understand how they go around doing that because a different technique that they are using. But that's definitely super interesting, and you should definitely look up into it.
Yeah, okay. So,
Yeah.
just to connect back to theory, if gravity is eventually described in a quantum framework, the idea of gravitons becomes more relevant. Maybe in the future we'll be able to detect it. Who knows? So, do you think gravitational wave observations could play, a role in bridging the gap between general relativity and quantum theory?
Yeah, definitely. That is, I mean, we know that wanting a theory of everything is what eventually everyone wants to have,
Wants
right?
to
I
have,
mean, yeah, we know nobody's happy with these discrepancies between quantum theory and gravity theory and all that. One way with which gravitational waves can help bridge this is by observing the or by okay how do we prove that something is right or wrong? We have an underlying theory. That theory makes predictions. We simultaneously develop technologies. The technologies are used to check if those predictions are seen in nature. And then we say, you know what, this is what is observed. That means this theory is correct. Check. Similarly, the quantum theories are having some sort of predictions of what would happen if a graviton would have mass. What sort of behavior would black holes do or gravitational waves have if gravitons had mass? Or so these sort of predictions are being done by theories. And now, using gravitational waves, we can check if these predictions are indeed followed by nature or not. I mean, in the end, what everybody is trying to do is understand nature. Nature is so beautifully complicated that all of us have to work together for generations and generations to understand it, right? So, in order to be able to get these theory or like have any potential of bridging these theories, one way that I can think of is to use gravitational waves to be able to check the predictions of the existing theories. So that is again something that I was looking into as part of my research in testing GR or in testing Einstein's theory of gravity. Is that certain, for example, if gravitons had mass, we would see certain signature in the signal. And one of my thing was, are we seeing such signatures? Are we seeing some information because of a massive graviton in this observations? So far there is no evidence, but that is one way I can definitely think of some bridging between quantum and gravitational theories.
Yeah, when you talk about this bridge, I just remember the concept of singularity. It's
Oh,
also an unanswered question. Is there a
yeah.
way you'd be able to find something about the singularity with these new findings about gravitational waves? Or is it another whole other thing? Like, do we need some other?
So the way I would think of singularity is it's a part of understanding black holes, right? Because that's where we see this nature of singularity. And with gravitational waves, we cannot look at single black holes. It's always a binary of something. So when it comes like that, that means we can understand the dynamics of black holes, but we may not so well understand the dynamics of a single black hole. So
Mhm.
in that way, based on what I know, I don't see how we would get more information about singularity. But indirectly, there should be some way. But I don't think I can think of one right now from the top of my head that I can say, oh, you know what, this way we can get closer to
Yeah.
singularity.
Yeah. Yeah, this has been a very insightful discussion. To be honest, I don't want to end this. I want to learn more. I want to talk with you
Yeah.
more about this. I'm very interested in this. And so, gravitational waves have clearly opened completely new ways of observing the universe, and one that allows us to study systems and processes that we were not able to do previously with the electromagnetic observations that we did earlier. And it's also very interesting how this field brings together fundamental theories and precision that is very unbelievable precision in engineering that is required for these detections and data analysis that is going on in such a direct way. So thank you so much, Dr. Purnima, for this insightful discussion. And we really appreciate you taking time to join with us. And yeah, thank you again. So over to
Yeah,
you.
no, thank you so much as well for this fun opportunity. It was really nice. I felt like all the questions were very well researched, and I had a really great time talking to you. So thank you.
Thank you.
Okay, so as we come to the end of today's episode, we would like to extend our sincere thanks to everyone who joined for this insightful discussion. And most importantly, a heartfelt thank you to our guest speaker, Dr. Purnima Narayan. That's like really like we are really happy because it was a very engaging and an interesting discussion. Okay, so Dr. Narayan, we are truly grateful for the time you shared with us today and for the remarkable work you do in advancing our understanding of gravitational waves and testing fundamental theories like gravitational forces and things like that. And your insights into physics of gravitational waves, their detection through experiments like LIGO and all, and their significance in uncovering the hidden dynamics of the universe have been incredibly valuable as well. And it has truly been an absolute pleasure having you on this podcast today. And at the same time, special thanks also go to Professor MLC Artigala, our senior club advisor, for her continued guidance, mentorship, and unwavering support. And we are also deeply thankful to Dr. S. Kandipan, our senior club treasurer, for her valuable guidance, encouragement, and dedicated support. And at the same time, we will also extend our sincere appreciation to Dr. R.A.D.D. Dharmasiri, our academic and inter-university advisor, for his academic insight and continued encouragement as well. And then we would also like to extend our wonderful thanks to our host, Ms. Kulamini Amarathunga, for leading this conversation so thoughtfully and helping us guiding through such an exciting exploration of astronomy and at the same time learning as well. And then we would also like to express our heartfelt gratitude to everyone who supported the success of this episode, both behind the scenes and in front of the camera as well. And of course, we hope this episode sparked your curiosity and encouraged you to keep looking up and asking questions and even exploring the universe with wonder. And with that, we conclude today's episode. Thank you once again. And we look forward to welcoming you all to our next episode of our next podcast series. Goodbye.